All right, here we go. So here's another problem. We're going to try to make them a little more challenging. So now I want to find the influence line for the shear at C. So let's go ahead and make a little choice. If I were to cut the structure here at C, which side of the structure do you want to work? You want to work the left side or the right side? Doesn't matter to me. Choose one. You want to go left?
So the X is
You can do that. Now remember, everything's measured X from left to right. You still want to do that?
Yeah.
Okay.
Why?
You want to go left? Yeah. Okay. So we'll go left. So if we go left, what do we need? We need the reaction at A. I'll go ahead and draw in the reaction at B. We may or may not want that later. So I'm going to draw a free body diagram over here. And I'm going to put my unit load at some distance x measured from the left. And I'm going to look at AY and BY. So I want the left side. I'm going to want AY. How do I find AY? Sounds like a good deal to me. So we'll take the moment about B and make sure it's in equilibrium. So starting with the applied load, what's the distance from B to it for an arbitrary x from the left? Looks like it's going to be 12 minus that. And what kind of moment will my unit load create about B? Positive or negative with right-hand rule? Positive. So there's the moment due to the unit load about B. And what about the reaction at A? And it has a moment arm of 12. So if you solve for A, you get 1 minus x over 12. Of course, I could plot that. That's really the influence line for the reaction at A. It tells me the reaction at A, as my load moves anywhere it wants, position x on the beam. So now I'm going to draw my free body diagram of the left edge. Now, since we wanted at C, I know this segment is 3 feet long. I know my reaction at AY is 1 minus x over 12. And I want to find the shear at C. The first case I'll look at is when my unit load is operating on that first 3. So I'm going to put a little label that says I'm between 0 and 3. That means my unit load is here. It can be anywhere it wants, position x. How do I find the shear at C? Let's sum the forces in the y direction. I'll assume up is positive. We'll make sure everything's in equilibrium. So what do we have? Well, I've got my reaction here acting up. That's 1 minus x over 12. My unit load is down, 1, and my shear is down. We'll solve for the shear at C. It looks like it's x over 12. Nope. Negative x over 12. Now, my unit load gets tired of running around here at 0 to 3 and decides to go somewhere between 3 and 12. So he's not on this structure anymore. So I'll draw it again. The shear at C is still positive down. My reaction at A is still 1 minus x over 12. Except my unit load has moved away. It's gone to the other side. So it's not on this structure anymore. So this will be when the unit load is between 3 and 12. And I'll sum forces again. So what do I get? I've got my force here acting up. That's 1 minus x over 12. And I've got my shear acting down. So I solve for my shear at C, and it's 1 minus x over 12. Bless you. Bless you again. So all I have to do is plot this. I'll plot this equation from 0 to 3, and I'll plot this equation from 3 to 12. So let's do that. So on the abscissa is the shear at C. On the ordinate are the limits of our problem, which are 0 to 3, and then 3 to 12. And I'll put a little demarcation here because that's where the two different equations have. So from 0 to 3, I plot this. So let's plot this equation here. So at x equals 0, what is it? 0. And at x equals 3, what is it? Negative 1/4. I'll plot that. Now I go over here and I use this curve, and I also plot it exactly at 3. What do I get when I plug in 3 here?
1 minus.
Get 3/4, right? You run it all the way out to x equals 12, you get 0. And why am I only plotting 2 points? Well, it's a linear line. I only need 2 points. The endpoints define the line. And there is the influence line for my shear at C. A couple things you probably might want to notice is what is the total change as this thing jumps up? Yeah, the change in shear here in the influence line is equal to 1. And it's always going to be that. And why is it 1? Because we're using a 1 for our unit line. You'll also notice that the slope of these two lines is the same. So what it says is I'm walking along. As I walk out towards C, I'm creating increasingly negative shear till I get to the left side of C, as close to C as I can get. The minute I step over C and I'm on the right-hand side, the shear changes sign in triples. Instantaneously. And then as I walk away from C, the shear decreases to 0. So where do I stand to create the largest shear at C?
Right side of C.
Just to the right of C. And what would I be if I weighed 200 pounds? What would the shear force be?
200 pounds.
200 times 3/4, 150 pounds. Now, usually in shear, we don't really care whether it's positive or negative. We just want the maximum value. So if you had to come here and splice this beam together, and you needed to put a connection there that could withstand shear, from me walking across it, you'd want to use the larger value.
Question.
Yeah.
On the second little three-body diagram from 3 to 12, why do you have your reaction from B on the left side and your C on the right side?
I don't. This free body diagram is the same for both cases. This is A, Y, 3 feet over there's shear at C. Remember, the thing that's moving X is the load. So from 0 to 3, this 3 does not mean the length of the beam. C is fixed at X equals 3. This X is where the location of my load. That's what that X is. So when I'm down here, when my load's on 3 to 12, it's over here somewhere. It's not on my left side free body.
Okay.
Elvis has left the building.
I don't get that reference, but...
You live in Memphis and you don't get Elvis has left the building?
Yeah.
Oh, that's terrible. It's terrible. Does everybody else get that?
Yeah.
Oh, duh. Sorry, Mr. Van Schilberg. We'll make fun of you later. Any other questions about that? Should we do something else while we're here? Yes?
Yeah, and you said that for the original, when you were solving for AY, it doesn't matter where you put X. I mean, where you put the unit load. You can put it anywhere along the road.
Well, okay, so when we solve for this, you see it's a function of X, right? So this gives me any value I want. For any X value I want, I get an AY. And what is that X value? What is X telling me? Does it tell me where AY is? No, where's AY? AY is at A. Is it moving? No. So what is the function of X? The location of the moving load. That's the function of X. So what I'm plotting here is the location of the moving load. I'm always at point C. It just so happens that point C is here at 3 feet. So it behaves differently before 3 feet than it does after the 3 feet. Maybe we should add something to this while we're here. What if we go back and also come up with the moment? So I'll add the moment to C to my cut. Can I find the moment in C? Sure I can. So what I do, I solve for the moment in this one, right? I'm going to have to write this down here. So from the first case, I'll call it case 1. If I now sum moments at the cut, set it equal to 0. So I'm solving for this moment. I'm solving for the moment at C as the unit load varies. So what is the moment here? That's positive. What is the moment for this moving load about C? Positive or negative? Positive. And what's the moment arm from the cut? It'd be 3 minus X. And then I have the reaction. What's the moment arm for that? 3. And that creates negative moment. So I have negative force, 1 minus X over 12 times 3. So what is the moment about the cut? Let's see. There's a 3, and then there's a negative 3. That cancels. There's a negative X plus 3/12 of an X. That leaves me what? 9/12 X negative, positive? Did I say that right? No, I did not. I did. So it should be, is that right? Yeah. So it should be 9X over 12. Does that seem reasonable? I think it does. Well, you put it to the other side when you solve for the. It comes out negative, but you throw it to the other side of the equation, it makes it positive. Okay, so now let's do the second case. So now I'm doing this free body diagram, and I'll do the same thing. I'll sum moments. So again, that's a positive bending moment, MC. I don't have a unit load anymore because what has happened, Mr. Tilburg?
It's moved to the right side.
Elvis has left the building. But what we do still have, though, the reaction at A, right? And it's the same. So it'll be minus, the force is 1 minus X over 12, and a moment arm of 3. So what is the moment? MC. It's all that. You could just leave it like that if you wanted to, or you could run the 3 through it, and you'd get 3 minus 3x over 12. So now, I could plot that. So here's the moment at C. On the ordinate, is that right? And now we'll check out our, is this the abscissa is X?
Yes.
Hey, I'm learning. This is great. I'm glad I came today. So from 0 to 3, I'm going to plot this guy. So when x is equal to 0, what do I get? 0. When x is equal to 3, what do I get? 9 over 4?
Yeah.
Well, let's just leave it at 9 over 4. And that's a straight line. What is this guy at x equal 3? It's 9 over 4. And what is this guy at x equal 12? 0. Where do I stand now to create the maximum moment at C?
3.
I stand at 3. So if I want to create the biggest moment at C, I stand right on top of C for this problem. And if I weigh 200 pounds, what's the moment I just created? 450 foot-pounds. See how easy that is? All right. Any questions about that one? Yes.
So, if there's nothing at C, what causes the jump in shear?
Well, remember, anytime we're even in our I hate to say this because I don't want to confuse the two, but when we drew shear and moment diagrams, what happened to the value of the shear as you went over a reaction? There was a jump. Right? So it's not uncommon to have a change. So what we've got here is, as I'm approaching from the left side, I'm creating negative shear at C just to the left. But just as I step over to the right, it jumps up to positive shear.
Right, but there's no reaction at C.
This is internal, right? Shear is internal. This is how the internal forces are behaving in terms of me. Now remember, simultaneously, as I move from left to right, the reaction at A is changing too. So as I move from left to right, everything in the beam is changing with my position. Right? The reactions are changing, the shear is changing, the moment is changing, everything is changing in this structure. Yeah.
So that graph would look different if we were looking at shear at like 5 meters.
Yep.
X equals 5 meters.
It'd be a different graph because we wouldn't be looking at the shear at C, we'd be looking at the shear at D. It's still going to have this same kind of jump as you go across it. It'll just be shifted to the right, and the numbers will be different. Same thing with the moment. What if I want to know the moment over here, say at 10 feet? You'll probably find out that the maximum moment at 10 feet will be created when I'm at 10 feet. Would it be the absolute maximum moment in the beam? I don't know. This just tells me the moment at C. This may not be the maximum moment in the structure. We're evolving towards that. We have to start slow, right? Don't you want to start slow and move instead of moving quickly?
I want to stay slow.
Any other questions? We're going to work some more of these.